For 5,000 years, every leap in human civilization was carried on the back of one simple idea. Take a strong metal, heat it, and add just a pinch of something else. Bronze, steel, titanium. Every alloy you've ever touched plays by the same rule. One main metal in charge, a few small helpers riding along. But in 2004, two scientists on opposite sides of the planet, who had never met, broke that rule. They didn't add a pinch. They threw in 5 metals at once, in equal amounts. Everyone said it would fail. Instead, they made the strongest, toughest, most heat-resistant metal humanity has ever produced. This is the story of high-entropy alloys, the metal from the future. To understand why this is a big deal, you have to understand the rule they broke. From the Bronze Age, through medieval steel, all the way to the modern jet age, every alloy has followed the same recipe. Take the aluminum in a Boeing 787 wing, the titanium in your iPhone frame. Steel, that's 98% iron with a tiny bit of carbon. Brass, mostly copper with some zinc. Even aerospace titanium is 90% titanium with small amounts of aluminum and vanadium. For decades, metallurgists believed mixing too many metals in large amounts would create chaos, brittle compounds, unpredictable structures, useless material. This wasn't even debated. It was treated as physical law. Then came Professor Jianwei Yeh in Taiwan, and independently, Professor Yeh Cantor in the UK. Both asked the same forbidden question: what if we just ignored the rule? Cantor's recipe became legendary. Chromium, manganese, iron, cobalt, and nickel, all in equal amounts. No boss element. Just 5 equals sharing the same metallic crystal. Theory said it should fail. The atoms should separate. The metal should shatter. Instead, when they pulled the ingot from the crucible, they found something nobody expected: a single, clean crystal structure. Atoms packed perfectly, behaving as if they belonged together. Today, we call it the Cantor alloy. And it kicked off the most exciting field in materials science in a century. So why does this strange recipe actually work? Scientists discovered 4 bizarre physical principles, what they call the core effects. Effect number 1, high entropy. Mix 5 elements in equal proportions, and the disorder, the entropy, becomes so enormous that the atoms actually prefer to stay mixed. Chaos, in this case, becomes the most stable arrangement. It's the thermodynamic equivalent of a perfect storm holding itself together. Effect number 2, severe lattice distortion. Every atom is a slightly different size. Imagine a parking lot full of cars of every model, bumpy, uneven, jagged. And that bumpiness is exactly what makes the metal strong. Cracks that normally spread through steel can't move, because the atomic road is just too rough. Effect number 3, sluggish diffusion. Atoms inside a high-entropy alloy can barely shove past each other. They're stuck, which means the material stays stable at temperatures where ordinary steel would soften, warp, or melt. And effect number 4, the wild card, the cocktail effect. When you mix 5 elements, you don't just average their properties. You get unexpected, emergent behavior. It's like jazz, 5 musicians improvising notes none of them could play alone. The result is a metal that defies prediction, even from the scientists who designed it. Compare it side by side with steel. In steel, dislocations slip easily. In a high-entropy alloy, they get stuck. These 4 effects, working together, are what make this material possible, and they're only the beginning. Here's where it gets crazy. In every traditional metal, engineers face what's called the strength-ductility paradox. Make it stronger, and it becomes brittle. Make it tougher, and it becomes soft. It's a hard ceiling. Cross it, and your part snaps. High-entropy alloys break that ceiling. A Cantor alloy bar will bend before it breaks, even under enormous loads. And here's the truly weird part. It gets stronger and more flexible as you cool it down. Drop it into liquid nitrogen, minus 320 degrees Fahrenheit, and instead of shattering, it absorbs more energy than any steel ever made. Which is why NASA is interested. Cryogenic fuel tanks, deep space probes, liquid oxygen lines. Anywhere ordinary metal would crack, high-entropy alloys thrive. Then there's the other branch of the family, the refractory high-entropy alloys, made from metals like tungsten, molybdenum, tantalum, and niobium. These don't even think about melting until you push past 3,000 degrees Fahrenheit. They're being engineered into jet engine turbines, into the glowing nose cones of hypersonic missiles, and into the cores of next-generation nuclear reactors. Compare melting points: steel, 1500 degrees. Titanium, 1670. A refractory HEA, well past 3000. That's not an improvement. That's a different category of material entirely. So where will you actually see these alloys? Aerospace, NASA, SpaceX, Blue Origin, all looking at HEAs for next-generation rocket engines. Parts that need to survive the temperatures of a small star without losing strength. Combustion chambers that can run hotter, longer, and lighter than anything before them. Nuclear power. HEAs have an almost magical resistance to radiation damage. Where regular steel becomes brittle after years of neutron bombardment, certain HEAs actually heal themselves at the atomic level. Future fusion reactors may be lined with them. Hypersonic flight. A vehicle traveling Mach 10 generates so much heat, its nose cone glows white. HEAs are one of the only material families that can survive it. Engineers test these alloys in plasma wind tunnels, recreating re-entry conditions on the ground. Biomedical. Some high-entropy alloys are biocompatible, corrosion-proof, and stronger than titanium, meaning bone implants and joint replacements that could last a lifetime. Dental implants, too, engineered to outlast the patient. Clean energy. Researchers are using HEAs as supercatalysts for green hydrogen production, splitting water into hydrogen and oxygen more efficiently than platinum. At industrial scale, that could reshape the energy grid. Motorsport. Brake discs and exhaust components for Formula One and hypercars are already in testing. Wherever heat, stress, and weight matter, HEAs are showing up. Even submarines and deep-sea vehicles, for hulls that resist corrosion at crushing pressures. Industrial pressure vessels, chemical reactors, defense systems, the list keeps growing. From microscopic wires to giant turbines, this family of metals is quietly reshaping every advanced industry. And we're only 20 years in. Now, the payoff I promised at the top. Earlier this year, a research team optimized a new high-entropy alloy, niobium, molybdenum, tantalum, tungsten, and nickel, using a process called atomic manufacturing. They tuned the structure atom by atom. The result, measured on a tensile rig, was extraordinary. A yield strength of 11.42 gigapascals, with 20% ductility. To put that in perspective, they didn't cast it. They architected it. Aerospace titanium yields at about 0.9 gigapascals. Premium tool steel, around 2. This new alloy is roughly 12 times stronger than aerospace titanium, and it still bends instead of breaking. That's not an incremental improvement. That's a generational leap. Papers are pouring out of labs in China, the US, Germany, and Japan. New compositions, new techniques, new records every few months. 12 times stronger than titanium. And the curve is still going up. Here's the most exciting part of all. There are roughly 10 to the 78th possible high-entropy alloy combinations. That's more than the number of atoms in the observable universe. Humans can't possibly test them all. So scientists are turning to AI. Machine learning models trained on phase data are now predicting which combinations will be stable, strong, and stretchy before a single sample is ever cast. Density functional theory, Kalford modeling, neural networks. They're compressing decades of trial and error into hours. Robotic labs synthesize and test hundreds of samples a day, each one a small step into an unexplored corner of the periodic table. We're not just discovering new metals anymore. We're designing them, the way a programmer writes code. Materials innovation centers are popping up across the world to chase this frontier. The next generation of aircraft, rockets, and reactors will be made of metals that don't even exist yet. Fusion power may finally arrive, built on the back of alloys we're inventing right now. And we'll be able to 3D print them, atom by atom, into shapes we couldn't dream of casting. For 5,000 years, civilization advanced one metal at a time: bronze, iron, steel, titanium. We may be living through the next chapter, and most people have never even heard of it. High-entropy alloys aren't just a new material. They're a new way of thinking about materials. If you found this fascinating, hit subscribe. I'm covering one mind-blowing technology every single week. Drop a comment with which application excites you most: hypersonics, fusion reactors, or unbreakable implants. Thanks for watching.